next, we're going to look at an example using what is known as the savings formula. So in these, we're going to make a periodic deposit, and we're going to have a periodic interest rate. And we're going to wonder what happens after a certain length of time making these periodic deposits. So here, you deposit $100 per month into an account that earns 1.8% per year, compounded monthly. How much is in the account after 5 years? Now, we can do this by looking at what happens each month. So let's do that. But we're going to do it, so if you imagine this is what, 5 years, here's the beginning, here's the end. In there we have 60 months. We're going to look at this for convenience sake. We're going to look at this starting at the last month. Because that last deposit, that last $100 deposit, will earn the least interest, and in a sense it'll be the least complicated to deal with. So let's just say after 5 years, the account has, and we're going to write it out, starting on the last month. Now, in all of these examples, I'm not going to write it, but it will be assumed that our deposits occur at the end of, in this case, they occur at the end of the month, so they do not accumulate interest. If it's you deposit $100 per year, we'll assume at the end of the year, just for convenience, so that the formula works. If you deposit at the beginning of the month, it would be a slightly different formula. So, month 60, you deposit $100, and it earns no interest. Okay. What about in month 59? Well, you still deposit $100. How much interest does it earn? Well, we use the compound interest formula. 100 times 1 plus the annual rate, 0.018, divided by the compounding periods, divided by 12. And for how long? Well, each one of these, well, not each one of these, this is what, m times t. M is 12, the number of compounding periods, times the number of years that it's been there. How many years has this $100 been in an account accumulating interest? Well, it's been in for 1 month. What's 1 month in years? Well, it's 1 month times what? 12 months, or times 1 year divided by 12 months. Month cancel, you're left with year. So it's 12 times 1/12. So this first piece is what, well, maybe I'll write it down. This is, let's say, month 60 deposit. This next piece, all the way over to here, is how much the month 59 is worth, because it earns interest on one of the months. Notice that exponent equals 1. What about month 58? Well, month 58, you still deposit $100, and it's still earning interest at this rate, 0.018, all divided by 12, raised to what? Well, it's still raised to 12 because that's the number of compounding periods. But how many months has this been earning? It's been earning, instead of 1 month, for 2 months, because it's in month 58. So it's been in there for months 59 and 60. So month 58 deposit. And this formula keeps going in the same manner. Notice the only difference between this term and this term is that this year's number went from 1/12 to 2/12. The next one will go to 3/12, and so on until you get to the month 1 deposit, which will have earned interest for the latter 59 months. So how much was deposited? $100 times 1 plus the rate. Should probably write that a little smaller. Should have written that a little smaller, actually. Plus 100 at 1 plus 0.018 over 12. 12 compounding periods, but it's been there for 59 months, which is 59 twelfths of a year. So all you have to do is add these 60 numbers together. Unless you have a nice formula you can use. Unfortunately, we do have a nice formula. I will tell you that this long sum equals, I'll put a large equal sign because I'm going to modify that equal sign in a moment. I'm going to do it over here, actually. Equals what? 100 times 1 plus 0.018 over 12, all to the 60, minus 1, and all of this goes over 0.018, no, 0.018, 0.018 over 12. So that entire sum equals this. Notice this rate quantity is still here. The rate divided by compounding periods is down there. And instead of any of these numbers, 0 through 59, we have a 60 here. This is approximately equal to what? 62.73 and 37 cents. Now, this large sum is equal to this. This is actually a Calc 2 result. It's a Calc 2 theorem. It's a reasonably large Calc 2 theorem on something called geometric series. It's toward the end of Calc 2. I'm not going to ask you for the a derivation of it. But it is a Calc 2 result that allows us to add these 60 similar looking terms together. Now, given all of this, there is a formula we could use that parallels this last equation. So let's write down the savings formula. And then let's do an example where we use the savings formula instead of writing out that large sum. Let's erase all of this. Let's also erase that last number for now. So the savings formula. So a periodic deposit D per compounding period earning interest at annual rate R compounded M times per year grows after T years to A equals D times 1 plus R over M all to the MT. I wanted to leave this on the board to point at it, but I'm not going to. This formula is more important than the minus 1. I didn't need to draw that low. All over R over M. So a periodic deposit D per compounding period earning interest annually R, compounded M times per year, grows after T years to D times 1 plus R over M to the MT minus 1 over R over M. And notice in this previous example, D would equal 100, R 0.018, M is 12, T is 5. So notice that exponent is 12 times 5. And that was all of the variables. So this savings formula is useful. We'll actually see it again in a slightly different context. Well, I guess it's really the same type of context, but a different type of observation will be required for it. But let's look at another example. And I'm just going to change these numbers over here. You deposit $5,000 per year into an account that earns 0.91% annual interest compounded. Let's change it to annual compounding. How much is in the account after 30 months? How much is in the account after 30 months? Well, for this one, we'll just use this savings formula. So I'll write the answer over here. A equals $5,000 times R is what? 0.0091. 1 plus 0.0091 all over M. How many compounding periods are there in a year? Well, it's compounded annually, so there's only one compounding period per year. So I'll just write that like that. All raised to the MT. M, again, is 1. What is T? Well, T is in years. This is 30 months. How many years is 30 months? Well, 30 months times 1 year, 12 months in a year, gives you 30 over 12 years, which is 5 halves of a year. So we have to the 1 times 5 halves minus 1 all over 0.0091. 0.0091, of course, M is 1. I won't write that. And this is approximately equal to what? 12, 585, and 44 cents.